be able to be as engaging with the audience as Brendan, but hopefully you'll find the presentation interesting. So I'm back talking about Canada One Water for another year. This time to reflect on phase one, which ended nearly a year ago in April 2024, and introduce phase two and try and frame it for the venue that it's being presented at, so in Ontario context. And quickly to introduce and acknowledge my co-authors. I won't iterate their names here. You can read them. And specifically identify Steve Fry as the co-lead in phase one, and in addition to Melissa Bunn as a co-lead in phase two. And of course, how do I advance my slides? There we go. The people on the title slide are not really doing all the work. We've got a great team supporting this endeavor that's drawn from academia, government, and Aquante. This is a reasonable reflection of the scope of the team and the contributions that they sort of operate underneath. Having acknowledged the team, we'd like to acknowledge how we actually managed to collaborate. And that's the funding that was originally provided by the Canadian Safety and Security Program of Defence Research Development Canada. And then was supplemented by the Geological Survey of Canada, Natural Resources Canada, and a number of programs there, the Canadian Forestry Service, Ag Canada, and NSERC through University of Toronto, University of Waterloo, and of course, Aquante. So a general sense of where this talk's going to go. I'll give you a little background, sort of where does this initiative set into a global setting, review objectives and modeling framework, and phase one and phase two content, and then a quick summary. And the global context is that Canada One Water was actually proposed way back in 1969. In fact, before 1969, it's documented in an annual report of the Inland Water Branch and the Geological Survey of Canada, where Alan Fries was then working. And to provide this in a little more context, so we're going to use Landsat as a baseline. It was launched in 1972, and how has the modeling world at sort of continental scale or global scales evolved since Landsat? And climate modeling really got going in 1969, and actually the originators and authors of that 1969 work won a Nobel Prize for their climate modeling. I keep pushing the wrong way. Global surface water mapping sort of really got going around 2000 as computational resources, access to Earth observation data, and ever increasingly AI started to come into play. And that was followed by continental surface water modeling rather than mapping. So looking at the water flux across the land surface, continental global scale. GRACE came on in 2002 and allows us to really look at the water flux of the continents in the globe. And then continental groundwater modeling, and you can see a number of names on the right. Maxwell for CONUS in the United States, and Chen, a PhD student at Waterloo with Ed Siddiqui, who modeled Canada. So the objectives of Canada One Water, and the point of that previous slide, just to reflect for a moment, is that we see Canada One Water as a multi-decadal initiative, and we're at the very beginning of that initiative, just like 1972 in Landsat. And you don't achieve the objectives that you seek out to in 1 or 2 years. It takes long-term sustained commitment. Nevertheless, the objectives of this phase one and phase two were to model the water cycle for continental Canada. They'll look at the coupled groundwater surface water system to refine the infrastructure, data sets, computational approaches. evaluate the potential influence of climate change on water resources to support decision makers at a range of community levels. And in phase 2 to generate water metrics for groundwater. And this just highlights where phase 1 was. It started in 2021. It ran to April 2024. It had 3 distinct sort of time periods within that 3-year frame of data assembly, model spin up, and model results. And it's documented in Open File 9190, a GSC publication that's available under an open access license, so it's free to download. And if you type in Open File 9190 GSC, you'll probably get a link to it. But you can also go to the Canada One Water website to download it. So we are trying to model the water cycle of continental Canada. Easier said than done. And how are we approaching that problem? And it's parsed into 3 different modeling frameworks and software implementations. In the center, climate modeling is the downscaling of global climate models to regional climate models, the integration of lakes, etc., is being performed largely through U of T and using WRF. And you can see the sort of grid cell resolution, and the orange box highlights the complete domain. Then we're looking at land surface processes and the community land model for evapotranspiration, soil processes, etc. And that provides a coupling between the regional climate modeling and the groundwater surface water modeling on the far right, which is being completed in hydrogeosphere. Canadian developed software from the University of Waterloo, and currently the, I guess, core of Aquante's business model. So model domain, we said we're modeling continental Canada to improve computational efficiencies, enable parallelization, both computationally, but also just from a human workflow perspective. We divided Canada into 7 large water drainage basins with respect to oceanic areas that they contribute to. And I won't iterate them here, but they range in size from 800,000 Baffin Island to 2.3 million square kilometers. And you can see some information on the finite element mesh and the number of elements per model. And then we're also looking at 70 watersheds of around 100,000 kilometers in size to help integrate GRACE analysis with the numeric modeling. And we have a relatively simplified concept, hydrostratigraphy. It's largely map-based, 2 soil layers, 3 superficial geology layers, and then 3 bedrock layers for the most part. And the surface mesh is defined based on 5th order streams currently, and hope to refine that to 4th order streams in the future. So the data assembly was a huge part of the first phase of Canada One Water. It did take a bit more time than anticipated. And here you see the range of data sets from digital terrain models to geological soils, hydrology, vegetation, climatology data, both historic and in terms of climate projections. And a lot of the effort involved not only compilation, but the synthesis of that data, harmonizing the data across jurisdictions, and reclassification or attribution of the data. And this slide, a version of the previous, just highlights the role NRCan plays in supporting the data for this initiative. Because some of you may wonder why I'm at NRCan and I'm talking about groundwater surface water modeling. Isn't that an Environment Canada responsibility? So our dream, our vision, and our hope, is that you will be able to access all of the data sets that underpin Canada One Water and the results through a cloud-based data portal that's currently up and running, and you can interrogate the data. There's only a small number of data sets you can download. In some cases, they're static. In this example here for precipitation, historic data, there is close to, I believe, 50 or 60 years of Canadian precip data. And you can actually use a slider here and look at the time series data also. Importantly, we believe that data sets need to be well documented, and that's one of the holdups in actually making the data publicly available, is ensuring that that documentation is in process. And then we're also documenting hydrogeological processes and data characterization. So I said we finished phase one, and we had contract deliverables that were provided. But you know, there's a big difference between publishable results and contract deliverables. And so we are continuing to refine some of those results. And this just highlights the calibration exercise for Ontario. It consists of 3 domains: the Hudson domain in the north, a small part of the Nelson River domain in the southwest, the Rainy River watershed, Lake of the Woods, and then the Great Lakes all contribute to the Atlantic domain. We're currently completing regional calibration work, and that's what you see here. And then we will focus in on more local or sub-regions to try and refine that calibration where it's not working so well. And you can see the Nash-Sutcliffe and the percent bias results on the right. We're getting pretty good calibration results from most of the domain currently. And the percent bias, we're looking at trying to maintain that or either side of the zero line within 20%. And I think that's looking pretty good. And these just highlight an annual calibration curves. The blue is the observed stream calibrations, and the dashed line is the simulation. Or sorry, I've got it the other way around. Observed is the dashed, and the blue is simulation. You see where this is a single year. We're getting good representation in terms of the seasonality, good amplitudes. Sometimes there's a little lag or an overshoot, but overall pretty good. And sometimes we're underestimating the total water flux here. And that sort of is what you're seeing here. Also in the percent bias, we're underestimating the water in the system a little bit, but within acceptable ranges, particularly at the large scale we're working. So phase two had 7 components, and I'm going to just introduce a couple of these. I believe indicator review, the Grace water budget flux, water budget closure, and the modeling and water indicators. Because we had hope. We did a summary or a preliminary review of indicators in groundwater and feel that there's a real absence of adequate indicators and particular indicators that have some kind of forecast capacity. You know, there's the drought monitor from Ag Canada using SMOS or SMAP, but it doesn't really have any, for soil moisture, it doesn't have a forecasting component. Grace can give you a lag of what's happening by 3 months, and we, once again, no forecasting component. And we're looking at, there are provincial monitoring networks, but the question is, what about areas where there are no monitoring wells? So we hope to address that issue and convert the monitoring and observation data into indicators. The Grace water storage flux, we have a lot of interest in Grace, and we're working closely with John Crowley at the Surveyor General branch on Grace processing, and Sushin Wang at CCMEO on the water component of Grace signals. You've seen John present at this venue in the past, and we're getting close to having a paper ready for submission, hopefully this year. It's been a bit of a chore. And you can see in the lower left some of the different trends in different parts of the country with respect to Grace and time series. And we're integrating that Grace work to help calibrate and constrain the hydrogeological modeling. Water budget closure with Sushin is both using GRACE, but also modeling using ANALCO, a land surface model, and really looking at getting away from just a total water storage or water flux estimate to also partitioning that into different components. We should actually have an update of water store flux trends for Canada over the last 20 years coming out in this calendar year. Modeling water indicators, then we want to be able to close the gap between the lag with GRACE data, which is 3 months approximately behind current day, and forecast GRACE rate up to current, and then project that GRACE signal through groundwater surface water modeling to 3 months in advance. And our target test area is Nelson River watershed. So what makes Canada One Water possible? Well, trans-jurisdictional data sets. The wealth of data that's being collected by any number of individuals in a myriad of organizations over time. The ability to harmonize data, accessibility of that data through open data and FAIR principles. So findable, accessible, interoperable, and retrievable. Proposal-driven funding. We couldn't have done Canada One Water without Defence Research Development Canada, which could have only been done with a Quante because we as a government agency can't actually apply for funding there. So collaboration's a key thing. Software maturity and computational maturity are both arriving to support this kind of continental endeavor, and a community of practitioners, which I think Brendan is really addressing in his earlier talk. So in summary then, I think the analog television screen of the 70s or 60s highlights where I'm thinking, you know, pre-2022, there's an incomplete framework and the state of groundwater is unknown. In 2024, with the completion of phase 1, we have a national framework. And as alluded to through the calibration slides, we have an emerging groundwater knowledge. And hopefully by the end of phase 2 in 2029, we will have national indicators and a national understanding of what's happening with groundwater on an annual basis. So thank you very much.